How's the first one look, guys? Pi bond, windshield wiper it over. Come in here, then we can move the lone pair in, make pi bond. Charge here, so we delocalize the charge to here, and here. Questions about those? How we do?
Should there be another methyl on carbon next to nitrogen?
Yes, there should be. Yes, this methyl right here, somehow it got lost. Yes, thanks for pointing that out. It should be a methyl. Because actually when I was looking at it, I was like, okay, it says more favorable than the one shown. The reason I said that is because if you move these down here, that is a resonance structure, but it would be very bad. And oxygen would hunt you down. So I kind of have to do that. Then I was looking at it just a second ago, and I was like, yeah, they're both secondary. That's secondary, that's secondary. Why is this one better? It's because I missed a methyl. I was going to draw it on the board. That ain't going to work. There's a methyl there. Now that's tertiary, where the original was secondary. Yep. There's a methyl there, and there's a methyl there, right? Is that right? Okay. Okay. Next one. Major resonance structure. Put electrons on oxygen. I did it all in one swoop. I skipped a resonance structure in between. You can't do that. For you guys, I'd recommend sort of one resonance structure at a time. If you just move these in and move these out, you would get resonance structure, a little pair here. You would get that resonance structure. But then if you come back with the next two arrows, move these here, and move these out, what does that give? It should give the one I showed. So you probably want to draw it stepwise, but then if you look at these three, which one is major? Negative on oxygen, oxygen being more electronegative. So I went directly there.
Yeah, if I did that the same thing, I just went directly to the OK.
Well, did you show the major resonance structure?
Well, that was the major.
Right. Like I say, you didn't have to show this. But I would probably, for you guys, recommend it because I just did it quick because I'm working a bad headache and I didn't want to draw the others. Question?
So when you're looking at the conjugate pi system, you only use one set of pi electrons?
There's only one conjugated pi system, and the answer is 6. If we draw the pi system, are you saying there's more than one conjugated pi system?
No, I'm just saying like you use one set of electrons.
Like, I'm not sure what you mean. We have p orbital, p orbital, p orbital, p orbital. One electron, one electron, one electron, one electron. That's 4. And then what's hybridization of this nitrogen? Well, anytime a lone pair is next to a p orbital, lone pairs want to be in a p orbital. So we want to make this sp2 and put one of the lone pairs there. And now you have these toy soldiers lined up and how many electrons are in there? 6. I know I saw a couple of people who got it. How many did you say? 10. Why? Which ones did you count additional?
I counted 2 in the bottom of the nitrogen, and then
really, we did this in week 2. If you graph the hybridization of every one of these atoms, you should have been able to do that in week 2, or hopefully. Then if you just look at, okay, how many are in pi electrons? This nitrogen is sp2. Since it's sp2, we have 3 hybrids and a p. What type of bonds do you see? Sigma bond to carbon, sigma bond to carbon. What else is there? 2 lone pairs. 1 lone pair is in a p, 1 lone pair is in a hybrid. But only 1 lone pair is in a p. See, there's the lone pair. The other is trigonal planar. boom, boom, boom. One lone pair, bond, bond. If you make the trigonal planar in the plane of the board, then the p orbital is actually coming out. Okay. How we do? Who got 6? You got 5? Well, it should be an even number unless it's a radical. There's no radical. Okay, well that's a good number of hands. Okay, one on the far right. I'll put the key up, you can look. Involves, you got to look at reacting both pi bonds. If you react the pi bond on the right, you get a tertiary and tertiary. But this is tertiary with resonance, with the ring here. Additional resonance. I mean, that's tertiary with resonance of the pi bond. This is tertiary with additional resonance of the ring. If you react the other pi bond, you're going to get secondary primary. Which is better? Tertiary and tertiary with resonance. So you get rid of this. You're going to react A, that pi bond. Then you can have chlorine adding here or here. Okay, we're heat, so we're going to get the most stable product. Which is most stable? If chlorine adds here, you get the product I circled. If chlorine adds here, which product do you get?
First one.
The first one. Okay, which is more stable? First one or the last one? Obviously the last one. Why?
First one's the one.
They're both trisubstituted alkenes. So why am I saying the last one's more stable?
The largest groups are
No, it's still governed by the alkene. Come on, somebody knows it. Why is this one more stable?
First one is stabilized by losing.
Which is more stable, a conjugated alkene or a non-conjugated alkene? Conjugated alkenes, double bond conjugated with the ring. Here, the double bond is not conjugated with the ring. Double bond conjugated ring, more stable. Like on the right, it's the most stable, it's going to be in one form. Conjugated alkenes are more stable than non-conjugated alkenes, right? Yeah? How we do on that one? You had a 25% chance of circling the right one, and nobody got it right? Thank you. Okay, that's just Diels-Alder. Zip it together, forget about the bridge, add the bridge back. These two groups are trans. You would also get an antigen because you can make that one dash, this one bold. How we doing? Acylium ion. You decide to cleave, you're going to get this cation, right? That's acylium, but I asked for the major resonance structure. So we want to draw here, triple bond, more bonds. Acylium ion. Major cleavage pathway for carbonyl compounds. How we do? Okay, key will be posted. See how you're doing. This week in lab, we'll meet downstairs, shaken, not stirred. We'll have a little bit of discussion. It's use of the subfunnel, it's a distillation. Any questions about lab this week? Group lab report due in lab when you come to lab, Thursday, tomorrow and Friday. Okay, guys. Substitution reactions, very important. We're focusing on SN2 right now. Okay, look at the headings. They mostly say SN2, although we did show the SN1 mechanism earlier. All right, and occasionally we will bring in a little bit of SN1. Mainly focusing on SN2. What's the problem with this reaction? You can't have your acid in E2, or your cake in E2. You can't have acid in the presence of base. Those are not compatible. So you could use H plus in the neutral nucleophile like methanol. Okay? All right, we'll pick up here. So, how do you make OH better leaving group? Protonated. What does that do? It turns the oxygen into a positive. Make it positive, then it'll want to leave. Okay? Now, later on, in a minute, we'll see another way to make OH a better leaving group. But the first way, and the predominant, major way, most common, is protonated. Protonated with what? Strong acid. Not with water, not with the weak acid, usually strong acid is what protonates something. Our choice, sulfuric. You can protonate with HCl. You can protonate with HI. What do we need up here? We needed an acid to make this a leaving group, to activate it. Then we needed a nucleophile to come in here and kick it off, do the substitution. Okay? Well, what if we react this with HI? HI actually supplies both, because it's a strong acid, so it supplies H+, but then the I- can be the nucleophile. And it's very common to react alcohols with HX, like HBr, HCl. And you replace the OH with the halogen. Now the mechanism can be either SN1 or SN2, depending on things. For example, this leaving group, it's not a leaving group as is, you first have to protonate it, right? We got H+. We'll find one that writes. These electrons become protonate the OH. Now that's not the favorite equilibrium. That's okay. Now we have I-, and we can act as a nucleophile, just like with alkenes, it acts as a nucleophile. Now sulfate will not act as a nucleophile, but we know the halides can. Because believe it or not, the things we learn and stress for alkene reactions are going to apply to many other reactions. Now this, we have a potential leaving group, check. Nucleophile, check. You know two mechanisms for doing this on a tetrahedral carbon. They're called SN1 and SN2. Which mechanism do we want to do here? Somebody? SN2. Can you explain why? Why SN2? Because the leaving group is on a primary carbon. If the mechanism was SN1, what would be our next step here? Ionization, make carbocation. Are you going to do that, make a primary carbocation? No, we said don't do that. So if you ain't doing SN1, what are you doing?
SN2.
There you go. How do you do SN2? Backside attack, kick that off. All at the same time, we showed the transition state. We talked about bond angles and stuff in the transition state. And what do we get? Well, we get what's shown. Iodine is now bonded to that carbon, and we kick off water. And that's a completely balanced lime reaction. We actually generate water in this reaction. By our good old SN2. I said this before. Students say, well, I thought SN2 was just one step. You're showing two steps. That's because the first step is not the substitution. The first step is just activation of a leaving group. From here to here is the substitution, and it was just one step. So, HX is a common reaction. And when you react alcohols with HX, what type of product do you get? Describe that product. Is it a ketone? What is it? Somebody? What's the general name for that compound? Alkyl halide, yes. It's an alkyl halide. It's an alkane with a halide. It's called alkyl halide. It's important to know what you're making because it helps you categorize things in your thinking, as opposed to just keeping it very bland generic and you don't have any markers to. Okay. Yeah, it's a common way to make alkyl halides from alcohols, HX. It supplies the acid and the nucleophile. Let's look down here. What if we react this ether with HBr? Okay, how do you make oxygen better leaving group? Protonated. Does it only work with alcohols? Or could it work with other oxygens? It can work with other oxygens. So, can you show the product down here? Now you would want to work through it mechanistically. You don't want to just pull a product out of the air. Take a second to show the product there. Okay, we've got H plus and Br minus. Can I just show this protonated? Okay? You should know. You should be able to show that. I'm just not showing that mechanistic step. Everybody can show how to protonate, get to that point with the mechanism? Okay? You got Br minus. What do you want to do now? We actually have a choice here. Up here, the leaving group was only bonded to one carbon. Here, the leaving group is bonded to two different carbons. Which carbon is the nucleophile going to attack and kick it off? Are we going to attack here and kick the oxygen off of that carbon? Or are we going to attack here and kick the oxygen off of that carbon? Which carbon do you want to attack? Okay, who says carbon on the left? Who says we should attack the carbon on the right? What about the other 90% of you? Okay, turn to the first page of this handout, look at the very top, it's in bold, and please read it. Not the scheme, the written part, the outline part. Substitution at what type of carbon? Okay, does that help you decide now? Which carbon is tetrahedral? The one on the left or the one on the right? Yes, the one on the right. Thank you. Attack here. Boom. Kick it off. What do you get? Well, the leaving group is left. When the leaving group leaves, it becomes what? That's the LG. And what else did we make? We have that. I mean, that left, so that's that. And when that's gone, we now have a bromine attached there, and that's that. Hope you can see that. Now, one or two said attack the tertiary carbon. First off, that's not a tertiary carbon. Tertiary carbon is attached to how many other carbons? Three. The carbon's only attached to two. But usually you only call things primary, secondary, tertiary when they're aliphatic or saturated, when they're sp3. So I wouldn't call that anything. But it's not tertiary. It's not tertiary because it's not attached to three carbons. But think about it. For those who said tertiary, by what mechanism would you attack here? Because if we attack there, I would have to refer you back to This over here, I put it in all caps. Never do SN2 with a tertiary halide. Well, halide is just the best leaving group. You can make that generic by never do SN2 with a tertiary, with a leaving group on a tertiary site. Okay? Arrows are a little bit off there. Any questions about that reaction? Now, question.
Would you also do an SN1 reaction since you have if you kicked it off on the left side, you would have a secondary.
Well, explain what I mean kick it off. Kick it off sounds like you want the nucleophile to kick it off. In SN1, the nucleophile doesn't kick it off. No, maybe that's not what you mean. So instead of this, let's go back to the propionated, pretend it's propionated, then move the paper. Instead of doing inserted here and kick it off, what do you propose?
If the ethyl and the oxygen left, and so you had a secondary cation.
Okay, so instead you'll do ionization, leaving group just leaving. That sounds like SN1.
Right.
You do this, and you get what? That cation plus ethanol, and then BR attack here. Problem is this is very bad. Also, you broke the rule at the top of the chart, of the handout, which is what? Substitution of what type of carbon? Tetrahedral. That's not a tetrahedral carbon. We're never going to do substitution there by SN1 or SN2. Reason is, that's a terrible cation. What did you call this cation? You called it... Yeah, but it is secondary, but it's different from this secondary. This came from like a leaving group tetrahedral carbon. Okay? Let's draw these in. What's the hybridization of that cation? This one. This one's sp2. This one's actually sp. Very bad. It's a double bonded cation. And if you think about it, it's worse than any cation like this. I can explain more, but that's important. The goal at the very beginning. You only do SN1 or SN2 at what type of carbon? Tetrahedral. It's a common mistake. That's a blanket message. We could explain why in different cases like this. Why is because that's a terrible cation. Even showed you that in mass spec and said that's a terrible cation. It's not conjugated. Okay? But you really have to know that because I see students all the time trying to do substitution adding non-tetrahedral carbon. So, it's a bad cation. That's why we don't want to do that. The only thing you really got there is an SN2 at the primary carbon, which is what we did, and this is the outcome. Now, what do? We started with an ether. What did we get? Can you describe this reaction? I mean, we made an alcohol. It's actually a common synthesis of alcohol, although it's sort of going backwards because we're breaking our molecule. This is commonly called cleavage of an ether. And if you look up reactions of ethers, one of the major reactions is cleavage. And we just did it. A common reaction is to cleave with like acid and nucleophile. And actually in Organic 2, we'll come back and revisit that when we cover the chemistry of ethers. And I'll say, hey, we did this in Organic 1. No different. But we just cleaved an ether. Okay. So you can make oxygen better leaving group by propionated. It can start with an alcohol, you can propionate that, but you can also propionate ethers. But here you have a choice of which carbon you're going to attack. Okay? And we'll define that more. Because later on, we may have a choice where they're both tetrahedral. And then we're really going to have to look at it, because both of them are really options then. But here, there was only one option, because that's the only tetrahedral one. That's not. Okay, another way to make oxygen a good leaving group is, mainly it's going to be starting with OH, is convert it to a tosylate, or mesylate or triphlate. These are all similar. Tosylate is the main one covered at the introductory level. These are also common. I'll just show them to you. Tosylate or the others will serve as leaving groups without the need for an acid catalyst. What is a tosylate? This is a tosylate. Everything, the oxygen, all the way through. Tosylate is a shortened name for toluene sulfonyl 8. A benzene ring with a methyl is toluene. It's toluene sulfonyl. And that's shorter to tosyl. And if it's anion, oxygen anion, it'd be tosylate. Tosylate is abbreviated OTOS. And actually, that's not correct, but that's the way I do it. More correct is OTS. I like to add in the O, so it looks like OTOS. Okay? All this, you need to know what a tosylate is. Now you don't need to pronate the oxygen here. It will serve as a leaving group just like a bromine or an iodine. So you can have a nucleophile, we'll call it minus, doesn't have to be. Come in here, kick that off. And we're doing a good old SN2, right? Backside attack. What would this give? Well, under my hand should now be nucleophile instead of this big old tosylate, right? So it's 1, 2, 3, then nucleophile. 1, 2, 3, and then nucleophile. But what was the leaving group? Well, these electrons move on to the oxygen as it leaves, and so that gives the oxygen double bonded there, and the aromatic ring, 2 lone pairs to begin with. But when this moves on to oxygen, how many there now? 3, and the charge of this is minus. What is this? That's supposed to be Greek letter like phi. That's generic for an aromatic ring. Okay? I just didn't want to draw that big old aromatic ring, but you need to know what a full tosylate structure looks like. Okay? You could also maybe put R. And R is this big old thing here. But something like that is generic for an aromatic ring. But this will serve as the leaving group. Why? Why will that serve as a leaving group, but hydroxide will not? Bad LG for rate determining step. Why will this serve as a leaving group? Yes. The fact that it leaves implies it's more stable. It's more willing to leave and exist. And I can say, well, why is it more willing to leave? And the answer is, what kind of stability do you see for this guy compared to something like that? Starts with a res. Resonance. You can show resonance. You can put this minus is spread over all these oxygens. You can also put the minus on that oxygen. Okay? And this is your OTOS. That's your OTOS leaving group. Okay? That's your tosylated leaving group. It will leave, and you don't have to protonate it because the leaving group is stabilized by resonance. And it's just as good a leaving group as bromine and iodine. And what mechanism did we do? SN2, yeah? Of course, because we're doing a primary carbon. We would never do SN1 here, would we? Okay, mesylate. It's the same thing. It's just over here, instead of having a toluene ring, you just have a methyl. And so it's methyl sulfonyl 8. And it becomes mesylate. You can also have a sort of a methylate trifluoromethyl. And that's called a triflate. And triflates are actually very good. They're just more expensive and not as common. The tosylate is going to be in your textbook. These others may not be. But it's the same thing. They're all good leaving groups. You attack this carbon, kick this off. Okay? Mesylate. Where did we see mesylate before? Very beginning of this handout. What did we see? Synthesis of Allegra, right here, 31 to 32. What do they have here? Here's your mesylate. They're coming in here with this nitrogen nucleophile. We'll see examples of nitrogen nucleophiles a little bit later. And they're coming in here, kicking off the mesylate. That's how they get the nitrogen bond in there. Okay, we'll see how to make mesylates or tosylates in a minute. Let me show you these two. A very common reagent and a variation of it is this. Now, if under my hands was H's, what would that be? That'd be H2SO4, the sulfuric acid. But with methyls there, it's called dimethyl sulfate. Because if those were anions, that'd be sulfate. If we put a methyl on each anion, we have dimethyl sulfate. It's actually a diester of sulfuric acid. That's the dimethyl ester of sulfuric acid. That's the diethyl ester of sulfuric acid. That's called diethyl sulfate. These are very common electrophiles. The tosylates are very common electrophiles. They mentioned the term electrophile. What are electrophiles like? They're like electrons. Okay? Well, we have a nucleophile that has electrons, like this, and it attacks this. So that implies that this likes electrons. If it didn't like it, it wouldn't want it to be attacked. Well, this comes in here, kicks it off. That thing likes the electrons coming in, so we call it electrophile. The thing with your leaving group is your electrophile. Likes the electrons to come in. Okay? So we can call these electrophiles. Nucleophile. Now look at this. If this over here was a toluene ring, a toluene, that would be a tosylate with a methyl. And pretend like that's a toluene ring. Our nucleophile could come in here and attack the carbon and kick off the tosylate. Well, it can also do it with this dimethyl sulfate. You can actually attack on either side because you can attack here and kick that off. But when you kick that off, you'll have an oxygen anion, which will be resonance stabilized. I erased my ring. But instead of a ring, we could just have like another O-methyl, and it's still a leaving group. But the reason I show these is because, especially dimethyl sulfate, this is very cheap and very commonly used. You can buy a big jug of this because it comes from sulfuric acid. Now you could also maybe, methyl iodide would work too. You could attack the carbon and kick off that leaving group. Methyl iodide is actually expensive, where dimethyl sulfate is very cheap. But these are analogous to tosylate. And actually, one of the labs, I don't know if we're going to be doing it next week or if I do it in Organic 2 or what. One of them actually uses diethyl sulfate. You just attack here and you kick off the leaving group. Questions about tosylates? This was the second way to make an OH a better leaving group. The thing about tosylates, though, is you make them and you purify them first, and then you use them. We're back up there when we did the acid. The activation of the leaving group occurred just in the mechanism. But here you would actually make this. Well, how do you make them? Shown here. You actually use something like tosyl chloride. That's where you have the chlorine bonded here. Then you have the toluene ring. And this first reacts here and displaces the chlorine to get this. Please look at this chemistry. It is a substitution reaction because we want to replace chlorine with the oxygen, but it's not SN1 or SN2. So that's not a tetrahedral carbon. It really doesn't matter that it's not carbon. The big point is it's not tetrahedral. It's got a pi bond. It is a substitution. Please look at this. You need to digest this. What bonds are here? Draw out your tosyl. Understand that. Abbreviation. We'll look at this. You make this first, then you come in with your nucleophile and displace it. Please also look at the stereochemistry. Bold to bold, why did it not change? Bold to dash, why does it change there? All that we've covered, but you got to digest it. We'll pick up there on Friday. And we'll be looking at other leaving groups down below. See some of you in lab tomorrow, guys. Have a good day.